That's great.
And my first question to start the conversation would be, I know that apart from the books, you've written a libretto to an opera. And actually what our magazine does is tries to unite science and art to popularize it. And my first question is, do you think that science and art have something in common?
Oh, I mean, I have a whole chapter in my book on knocking on the door on creativity and what science and art have in common. I mean, there's quite a bit in common in the sense of how we approach things, and sort of. I mean, different people have different approaches, but a lot of the time it can be problem solving. It can be bringing in many ideas that you have in your head that you try to make some sense out of, so you come up with some sort of coherent story about them. I mean, there is a big difference with science, which is that it is in principle testable. So an idea can be right or wrong, whereas there's a bit more freedom in art to say that it could be different possibilities. Nonetheless, I think it's, I mean, I was surprised, especially when I wrote my books even, how much people who were writing thought this is in similar ways in terms of making sure there's a common thread, that it logically follows, that there's a sort of, but one of the reasons I wrote the opera though was because of the, well, first of all, because Hector Parra contacted me. It wasn't my idea. But also, I had just spent an enormous amount of time trying to figure out how to tell this story in a linear fashion, about the science. And it was kind of interesting, the idea of having many different voices at once. The opera, I hadn't thought about, I mean, you're not teaching, but you're sort of introducing people to the concepts. So, you have visuals, you have music, you have different musical lines, you have different voices, libretto, you have sets. It's just a very different way to try to just get, and I think it succeeded in the sense that it got people aware of issues they wouldn't have been aware of otherwise, including even people who were at the Pompidou Center. So it was quite fun.
Thanks. And so what I also wanted to ask is that in one of your interviews, you mentioned that your day looks like you're writing in the morning and you're doing science at night. So can you tell more about the life of the particle physicist?
Well, I mean, that was when I was writing books. I mean, now it's actually in the coronavirus time, everything's up in the air and everything is a little bit different than it usually is. But I guess the point is that, I would sort of stay home and write a little bit and then go to the office and then interact more with colleagues and think about. So I sort of like to have separate places for different, I mean, it doesn't of course work, but I like the idea that I would write at home and do physics when I was in my office so that I could separate them. Of course, now everything's at home these days, so I don't know. What is it like there actually, where you are?
Yeah, we also are, we're working from home. Here our team works from home, but now this week actually it's a little easier for some places opened up, but still have limitations for people that can be there. So obviously the universities are closed and all the curriculum postponed. So the whole world is in this boat. We're all together in this. But
and how many cases have there been, or is it accurately reported?
We have the decrease. As far as I checked, each day I think around 500, 300 cases are added.
That's quite a bit, actually.
Yeah, mostly in the capital of Ukraine, but in other cities as well. But it's decreasing, which is good. Hopefully it's going to keep that way. But because of the economics issues, the government decided to open up some of the facilities.
And the hospitals have been able to handle the caseload so far?
Most of them, yes. But their death is obviously, but mostly, yes. They have enough. I'm not sure if they have enough tests. That's what, like,
no one has.
Everyone's lacking. Yeah, but
it's scary to open up before we have tests, I have to say.
Did it change for you? You are doing your work remotely, or is it opposed?
Everything. Or is it what?
I mean, is it on hold maybe for now?
I mean, we're trying to work remotely. I mean, obviously there's different types of distractions, and this would be the time that a lot of conferences would happen. So obviously those aren't happening, although there will be one online conference, or a few online conferences. So it's not like everything's stopped. but it's definitely different. It's actually, for me, it's really interesting because I haven't been just home consecutively for a long time. It's just interesting watching the seasons change and the birds come out, and it's kind of fun.
Yeah, and you mentioned that you are not writing right now, so you're not planning on a new book.
Not right. No, it was a bit overwhelming to do everything, and I thought it was a good idea to try to focus on physics and frankly I mean, this would be a good time to be writing in principle, but also it was a good time just to sort of reset and think about, I've just been traveling so much that I didn't have everything work in order, so I thought it was a good time to try to do that a little bit more than I usually do.
Yeah,
and to do some physics. Mm-hmm.
And I wanted to, I'm pretty sure all the readers will wonder how that day of particle physicists, maybe the normal day, not the coronavirus day, looks like. I mean, we've tried to picture the scientist in the lab, the biologist who works with the microscopes and all the samples and everything, but you do a lot of theoretical physics. And how do you structure your day? How much does reading other scientific papers take time? How much writing articles to publications take time? Can you tell about that?
There's no single answer, and I mean, some people probably are much more scheduled, but I think when you're doing creative work, it could be many different things, and you could get excited about an idea. I mean, there's a lot. Some of it's on your own, some of it's working stuff out, reading papers, like you said. Some of it is talking to people. So I really enjoy when I go to the office and talk to the other postdocs and students and some of these other professors and hear, just bounce ideas around, and then what to think about when you go back. So it's not like it's one thing. I mean, you might wake up in the morning and do it, or you might just do it in the afternoon, or you might be up late at night. Different people have different times, and I myself have changed over time too. So in different phases, I'm doing it differently. So there's no single answer, but it does involve all those things. It involves working stuff out. It involves writing stuff up. It involves reading papers and talking to people and seminars. There are a lot of seminars too, and conferences, and which also offer opportunities to interact with people. It's less isolated than people imagine a lot of the time because there's so many conferences and talks, and sometimes that helps stimulate ideas, and sometimes it gets in the way. And so what's interesting about this time is it's forcing, it's interesting to see how much people like resort to Zoom and how many people try to avoid it and just take advantage of the time to be on their own. I think it's people have an opportunity to work differently now, and some people take advantage of that, and some people are happy with the way they work and want to just continue that way.
Thanks. And as a follow-up, when do you get your aha moments? Like, do you remember when you got the idea? That's what we started from, the creativity process. I know it's artists do, right? But can you remember?
It's not always just one idea. I mean, a lot of the time, you'll be home thinking about things, and something will just kind of click. But a lot of the time, some of the ideas came out of actually looking at the equations, like the idea for our warp geometry. It wasn't like we looked for it. We were trying to solve some other problem, but we were just looking hard, and we looked at it and we thought, this looks really strange. And then your aha moments come back and forth with, oh, this will work, trying to figure things out better. So it's not like one answer. So.
You started, I listened to some of the interviews, and you mentioned there that your love towards science came through math, right? But how did you find yourself being a particle physicist, this particular sphere of physics?
I mean, I think a lot of it, some of it had to do with my advisor, Howard Georgi. I just liked his style. And he had a really great group of really brilliant people, including Ann Nelson, David Kaplan, Andy Cohn, Anish Manohar. It was just brilliant people there at the time. Steve Sharp was around. It was just great. So there were so it was just sort of inspiring, but also I like doing things. So I like the kind of puzzle solving aspect of it. So, I think it's a question of style. It's a question of interest. It's a question of, trying to do something that might have some longevity, but you don't always know if it will. So I don't think there's one answer.
And Also, you mentioned previously that scientific context influences your research, right? As correct me if I'm wrong, but you first worked more on string theory, if I'm correct, and then you are now more focusing on dark matter right now.
So that's kind of a misperception. You know, I started off actually doing what's called model building, trying to understand features of the beyond the standard model. Then actually as a postdoc, I moved to Berkeley and became more interested in experiments that were going on, and had some insights into how those experiments could be interpreted, although at the same time I was doing some cosmology as well. So not just that, and some model building. And then when I was a professor, I became interested in some formal aspects of supersymmetric theories, and to some extent in string theory related things, but it really was again from a model building perspective, although some of it did overlap for sure with what was going on in the string theory community. And recently I've done a lot of more cosmology and some astrophysics, just because that's where data is. And I do like to be where you know, I think it stimulates new ideas, and I think it also is somewhat rewarding when you think your ideas can be tested. So it's kind of a combination.
Yeah. So
it's been all over the place. Right now I've gone back to thinking about extra dimensions, which I hadn't planned on doing in string theory a little bit. So, you know, it changes over time. Did some gravity things recently, some dark matter stuff. And, you know, one of the nice things about our fields is that we have the flexibility to change exactly what we're doing and develop new fields of expertise.
I know it's will be hard but very poetic theories, and our readers would be also interested in this. For me personally, as I read about it a lot, but it's still hard to understand it quite well. If you could maybe explain briefly string theory. What I mean by that,
I don't like doing. I mean, I don't work on string theory, so you should ask someone else. I mean, I could explain it, but I mean, I prefer to talk about things that I think are more testable. So I mean, I'm doing things related to string theory, but the question I'm interested in string theory has to do with why we seem to observe dark energy in the universe, or what's called de Sitter space. So I'm interested in sort of, you know, it's not quite practical, but a little bit more applied and sort of. I mean, string theory gets a lot of attention, but I think also beyond the standard model stuff and cosmology and things are really interesting, and I prefer to focus on those.
Yeah, what I was leading to, I understand what I was leading to is that it's ultimate prize, yeah, also correct me if I'm wrong, to unite the quantum.
No, that's what string theorists say. I don't think it's, if you read my books, you'll see that I'm not a very big fan of thinking of it like this.
No,
I think that we should build things up. Yeah.
Yeah. Once again, I'm just going to explain myself. What I meant is that still scientists all over the world, not only with the string theory, they are working on understanding how to unite quantum mechanics and theory of relativity. Right? No.
No, that's what I'm saying. It's not what everyone works on. Some people work on this and some people don't. I mean, you know, that's a very top down. I mean, it gets a lot of attention, but there are much more immediate problems, because those are things that are beyond the scales at which we can test things. So for me, it's much more interesting to kind of build up from where we are and see how we can get the next step. I think it's unrealistic to think we're going to have an ultimate theory. I think it's a good playground to work stuff out, but I think it's really interesting to ask, you know, well, what can we learn from black holes? What can we learn from dark matter? You know, how can we explain the dark energy in the universe? So that is my area of focus.
Let's talk about that then. I love your example in the book. Actually, I think it's a great metaphor. You explained the dark matter as a celebrity, right? That someone gathers around it, but you don't know who is there, but you for sure know there's someone famous.
I like that analogy too. Thank you.
And also, I think that struck me so much. This, and you mentioned that it sounds like a joke, but it's really true that you can find. If you're looking for something, you can not find it, but you never find nothing, right? And I wanted to ask you about that. A lot of people obviously ask you, maybe scientists are wrong, maybe nothing exists, and dark matter is a mistake or something like that. And you mentioned that in your talks that it does exist. Can you explain a little bit more about that?
Well, I mean, so dark matter, it's, first of all, it's not something that's so crazy to think would exist. I mean, it's matter, which means to say it clumps, etc. It interacts with gravity like matter, but it doesn't have the same charges or interactions with other forces. So it's basically saying not everything is made up of atoms, not everything is made up of protons and neutrons or quarks. I mean, there could be other particles out there in the universe. And the reason we don't know about them is because we don't interact with them a lot. We interact with them only gravitationally or very weakly somehow. And so it kind of explains why we wouldn't have seen it. And it also, there's no reason to think that everything is just like us, that everything is made up of the same stuff that we're made up of. So, but the reason we think it's there is because it's been measured in many different ways, and they all agree. When people try to come up with alternative explanations, they usually can explain one or two of the things that convince us that dark matter exists. But there are many reasons we think dark matter exists. I mean, one is the one that was originally done, which is it explained the rotation rates of stars in our galaxy, which required more matter than we could see. And similarly in galaxy clusters, bound states of galaxies, you need more matter than can explain the velocities we see. There's gravitational lensing, so there's stuff that you can see the effect of matter on light, and some of that matter is dark. There's something called the bullet cluster, which looks like it's the merging of different clusters, where it looks like the dark matter went through and gas stayed in kind of central. Even the cosmic microwave background radiation, the details show us that there's dark matter because we see the acoustic oscillations. So we see stuff that gets pulled in by gravity, pushed out by radiation. So we see not all of it gets pushed out by radiation, a lot of it is dark matter. And even the very existence of our galaxy in the lifetime of the universe at the size of our universe convinces us there is dark matter. We wouldn't have had enough time to form our galaxy if there had been less matter. I mean, there's 5 times as much dark matter in terms of energy as ordinary matter. And we wouldn't have had enough time to form the galaxy. Plus the size of the galaxy is such that it would have been washed out by radiation if there had been dark matter. So there are all these different pieces of evidence that point to the same thing, and they all point to the same amount of dark matter. So it's rather compelling to think that it exists.
And in your book and in your research, in your book, you mentioned a lot of different explanations, possible theories for dark matter. And I wanted to ask, maybe you lean to one of them. Maybe you have a favorite one, and could you, or a couple that you think are the most plausible ones?
You know, until we have experimental evidence, I'm not willing to put my money on any of the horses. You know, I don't know. I mean, I think that, you know, a lot of people liked WIMPs because they thought they could find them, but no one found them. So they're still looking, but it doesn't mean that they exist. WIMPs being weakly interacting massive particles, particles that do have some small interaction with our stuff, but just not as big as ordinary matter. But it could be lots of different things. It could be parts of other sectors. It could be just other matter that has nothing to do with anything we know about. It could be some particles called axions, which are very light particles. It could be light dark matter. It could be interacting dark matter. There's so many possibilities. You know, what we can do as theorists is try to find new and novel models and new and novel ways to look for dark matter if it takes different forms. But like I said, I mean, it's really all it requires is a stable particle with a certain type of interaction that allows enough of it to be around today. And that's not that hard. I mean, that's not that, I would say, I don't know what I mean by hard, but it's not that exotic in some ways.
Thanks a lot. And obviously the name of the book, the last book, Dark Matter and the Dinosaurs, I want to talk about that. It seemed to me it's like a butterfly effect in the popular culture that something caused a dinosaur extinction. But I'm just very interested how you stepped upon this idea.
Well, we really were, I mean, it's a nice example of science in action. Because what we really were trying to do at first, along with Matt Reese, D.G. Fan, and Andre Katz, was explain some weird observations that had been made by something called the Fermi satellite, where they seem to exert see more photons than you would expect. Now, why was this strange? Well, they didn't see the charged matter, but they saw lots of photons. And so none of the obvious models worked. And we were trying to find ways that you can get something. But we realized what you could have is matter be much denser, dark matter be much denser than we thought. And one way you can make dark matter much denser is by having it radiate the way ordinary matter does. So if our matter in the Milky Way is much denser than dark matter because it's collapsed into a disk. So we just started thinking about a dark disk, and in sort of the early days of this work, I happened to be giving a talk in Arizona State University, and Paul Davies was in the audience, and he said, "Oh, so you could explain the extinction of the dinosaurs?" And I was like, "What?" But it turned out there had already been a theory, not using dark matter, having to do with periodic extinctions, or let's say periodic meteorite strikes. So periodic strikes in the scale of like 30 or 35 million years of big, massive objects from what's called the Oort cloud, from really the outskirts of the universe, things that become long period comets. And so the idea is that every once in a while, so these objects are thousands of times farther away than the Earth is from the sun. So the idea is that every once in a while, they're very weakly bound. So any kind of gravitational kick or any kind of kick could in principle kick it out of its orbit so that it leaves the solar system altogether or comes hurtling down towards the center. So those would be enhanced times of possible meteorite hits when things are coming towards the center. And so the idea is that the solar system is going up and down as it orbits the Milky Way. So if every time it crossed the Milky Way plane,
there's a problem with the internet connection. Yeah, there was a loss of connection for a while, but now we can hear you as well.
I know. I'm getting some funny buzz though.
Do you have it still right now?
Okay, it just went away. What was that? Do you know what it was?
No, I think it's something with the internet connection, and but now we're back on track. Now we're. Okay,
good. Okay, fine.
So you were interrupted. You were talking about.
Yeah. So what I was saying was that the ordinary explanation. Well, one explanation. First of all, we don't know for sure that it's periodic. But we do know that it was a big meteorite that killed the dinosaurs 66 million years ago, which is pretty cool and interesting. So we checked for periodicity. We also checked what kind of dark matter disk. So our dark matter disk could add density, could be denser and narrower. So it could be more sudden, and there could be a different period for the solar system, both of which go in the direction of letting this explanation work. So we just worked out the consequences and what you would need for the dark matter disk for this to be true. So it kind of gives you, it's nice because it gives you a target for what you'd like the dark matter surface density to be. So there was some science behind it too, like we could work out, what the likelihood is and whether we might hope to see it. So it's pretty exciting.
It is. I wanted also to ask you about the next frontiers, the ones that you're looking to in research and maybe in the data. Where you can get it, maybe you are expecting it to come from the Large Hadron Collider or from some space telescope. Can you talk a little bit more about that? What are you looking forward to in your research?
So I'm glad the Large Hadron Collider runs, but I'm a little bit afraid it might not have high enough energy. So I really hope there is a higher energy machine in the future, because I think a lot of the things we're interested in might require higher energy. I do think that some of the measurements about dark matter on smaller scales are interesting, but also I'm very excited about gravity waves. It's really hard to test new physics with gravity waves, but I like the idea of comparing what you can see with LIGO, which we have on Earth, to LISA when it launches in the future, and whether you can tell things like if orbits are eccentric, for example. I'm also doing some more theoretical work right now. I'm thinking about what it takes to get de Sitter space, to get dark energy, and trying to understand that. And also just, I've actually gone back to thinking about brains and just, so we're looking at moving brains with the collaborator Andreas Kart, and also thinking a little bit more about inflation and if there are ways to distinguish different inflationary cosmologies. So I'm using this time to, play around a little bit with different ideas. So we'll see which ones come out.
Oh, that sounds cool. Can you explain to me, because I don't quite understand the inflational cosmology. What is it about? It sounds very interesting.
You've heard of the Big Bang cosmology, where we
of course.
Yeah. So inflationary cosmology involves perhaps a much faster and accelerating universe in the beginning. So the expansion factor is accelerating rather than decelerating. So it could be like exponentially expanding. It's basically an explosion in the beginning. And it's nice because it sort of says that everything talked to each other in the beginning. The regions that are causally connected are much bigger than we would have thought. And there's a lot of evidence for this kind of phase in the universe, because we look at the cosmic microwave background and we see evidence for the kind of fluctuations that inflationary cosmology would predict. So the question is, so basically what you want is something essentially where there's some large energy density in the early universe that then goes away. And then it reheats back to standard Big Bang cosmology. So it's challenging to think of something that could be there, then stop, and then reheat in a way that it lasts long enough. So there's many challenges to inflationary cosmology, and there's no completely satisfactory models. So it's really interesting both to think of models and to think of ways to distinguish among them through experiments and data.
Thank you. And another question is, what questions actually do you want to get answers to during your lifetime? What are the ones that you will, maybe a couple that you would love to know the answers to?
That is a very nice question. It's too big a question to answer right now. But I do, there's a lot of things we've been working on, and they're not necessarily the biggest questions, but I guess I really do want to know, what it is that solves the hierarchy problem, why the Higgs mass is what it is. I would like to understand dark energy better, and I would like to know if there are additional dimensions of space. So there's, but there are many questions I'd like to answer.
Okay, thank you. And for now, I want to pause and give a chance to our readers maybe to chip in and ask questions if you have, because I have more, obviously, but maybe at this point when we're talking about dark matter, dark energy, and cosmology, and I wanted to talk more about science in general and scientific way of thinking. Richard Dawkins, he in one of his books, he wrote that he hates when people are approaching science with a he called it non-stick frying pan approach, that you have to have practical things out of scientific research. And he actually compared it with making music, that it is an exercise for violinist's arm. That you should do science for the art of science, right? For the science itself, not for some practical implementations, which many people approach science in that way. Theoretical physics, it doesn't get, obviously it doesn't get like short-term results. It's a long way path in order to understand our place in the universe, in order to understand ourselves better and universe, obviously. So I wanted to ask, what is your approach towards science? What do you think, why do we need science?
I certainly am not looking for practical applications, although I'm very happy when people do. I think, look, even the things that, actually probably some of the best practical applications we have came out of people doing very theoretical work, because they were major breakthroughs. They were different ways of thinking. So basically anything you can name almost anything you can name that is a really great application of science was not done specifically for that. Drug discovery is a little different, but even a lot of drug discoveries have been accidental, and some of the most major ones certainly were. But almost any other thing you can think of in science was some major theoretical development that then, it's true, people then hunker down and figure out how to apply them. But underlying that was some major theoretical breakthrough.
Thanks. We have a question from a reader. Is there any recommended popular literature that you like, or maybe the YouTube channels or some other sources that you...
Look, I wrote my books because I like I mean, I thought I had a way of saying things that other people hadn't said. I mean, there are, of course, some good books out there. It depends on your style and what you... But I've written three and a half books, and I think they all really have quite a lot of information, a lot of introduction to a lot of different subjects. So I like those.
Okay, well, one more question, and it might be more theoretical. What do you think about Verlinde's theory of gravitation? I hope you understand.
You know, there's just a lot of things that even if you believed everything he said, there's a lot of things that are yet to explain so far. So it's hard to see how it's consistent. Like I gave you this long list of things about dark matter, for example. It's hard to know how it could possibly work with you know, time-dependent cosmology, for example, or things moving. So, you know, it's nice that he's thinking about interesting ideas, but it would need to be fleshed out a lot more before we can really make a judgment.
Okay, thanks. And more. Professor Rendal, do you think there are perspectives for the HEP cosmology-linked experiments in unorthodox setups, for example, cold atoms or condensed matter in general?
Oh, definitely. A lot of people have been thinking about these things, especially a lot of this work has to do with either kind of gravity waves or axions, which are very ultralight particles. So things that have long wavelength. People are thinking about ways to test them, and they're really clever ideas. And axion searches through NMR, etc. It's really clever ideas, and so or I guess axion-like particles, very light particles that interact with photons, for example. So there are definitely some interesting. I don't know if I call it unorthodox, I would just call it more tabletop. You know, it's just, yeah. But I mean, it's not like it's going to test everything. It's not like it's going to be the high energy frontier. But there are particular cases where it could give us some really interesting information.
Thanks for that. For now, we don't have more questions from readers. I hope we get more, but I come back to the scientific way of thinking block of my questions is that you also mentioned in the book that the cosmological understanding for lay public is very important to re-evaluate our approach to planet Earth. Maybe you can tell more about that.
Well, I think the coronavirus has made it really clear the importance of scientific thinking and what happens when we avoid it. I mean, places that have done the best are basically places that have been more scientific in their approach to the crisis, and places that have done worse. So, you know, so when, you know, or people that did science too late or didn't do it at all. And so, you know, every day we confront this in the United States, you know, this sort of scientific versus anti-scientific ways of thinking. And, you know, sort of there's other things that come up with that, you know, short-term versus long-term, logical versus not logical. There's many different ways you can categorize things, but clearly a lot of the problems to address, you know, it's not the only consideration. I mean, you know, there are social considerations, economic considerations, but one has to really do this, even those scientifically in the context of what is the overall best strategy. And look, it's not like there's always a numerical answer. It's not that I'm so simplistic to think that, but I think having this kind of way of thinking in the back of your mind is extremely helpful when evaluating the road forward.
Thanks so much. Also,
I also think that it's up to the scientific community to kind of support the people who are out there talking about science, especially in the US, where these people seem vulnerable, oddly enough. And so I think it's really important that people stand behind these kind of approaches.
I also wanted to ask about you as a science writer, because at least in Ukraine, we get that a lot, at least from what I know, attitude towards scientists that if they do science popularization, then they have less time for doing research. Did you ever was treated with that attitude or had the threat that you may be dedicating less time to your research or something like that, does this context exist still in the United States? Because also from what I read, famous Carl Sagan, he was also treated like that he did a lot of popularization, then his research suffered or something like that.
So it's, first of all, it's true. If you're doing a lot of writing and giving talks, it does interfere with research. It's hard. I mean, I did both at the same time, but it does take a hit. And it's one of the reasons I'm not writing right now is I wanted more time to focus on science. And I realized, if I kept doing that, I also was just working all the time. One way of dealing with it is just doing twice as much work. But at some point it's hard. Because especially with books, you have a different schedule and things like that. I think people were less direct about it, but I think there was probably some antipathy to it. I think there was some jealousy too. People I think that it's easier than it is and less work than it is sometimes. But frankly, as a woman, it's hard to know like what attitude is underlying any particular reaction people have. So, so I think people are quick to make judgments before they even, they'll say that you're not working, but the fact is they see things that are more visible. So the public stuff is by definition public, it's more visible. So you could be doing lots of research, and no one knows about it. So it's not a very realistic assessment. So very few people make this judgment who are actually qualified to make it.
Thank you. We have more questions from readers. What is opinion on degeneracy and observation in both modern particle physics and cosmology? With no LHC successor or of LHC invisible future, where one would find new knowledge in this field?
Well, so one of the reasons I'm working on cosmology is because I think there is some new knowledge to be had. Of course, we would also like to see a higher energy collider, which would be great. There's also precision measurements, which I think are very nice, that do indirectly probe higher scales, because if there is stuff at higher scales, it can affect things if we measure precisely enough. So there's a number of different directions that can give us more knowledge, but indeed it is frustrating that the LHC has the energy it did. If we built the SSC, we would be in better shape. I think the superconducting supercollider would have been a more realistic to cover the energy regime we'd like to cover. So there is a hope to get to higher energies. But in lieu of that, I think cosmology and precision measurements would be the way to go.
Thank you. If you have more questions, I'm asking our readers, you have almost last chance to ask them, because I have the last one is about you as a writer. A lot of writers have written blogs. They have, have you ever had that? And maybe how do you organize your writing? Do you do research first? You then write? Can you tell more about that?
So my joke is kind of like, I don't have writer's block in part because, I'm sort of sneaking in to write. So it's sort of like my treat in a way. I'm sort of exaggerating, but, because there's always something else to do. So I'm always happy to find the time to write. I have a trick, which is when I do get excited about something, even if it's not like where I am in the book, like I write well in advance of some chapter. So when I get to that subject, I've already written something. So there's a starting place. I'm very rarely looking at a blank page, because when I'm excited about something, I'll write it down. So I sort of know where I'm going a little bit, although obviously afterwards there's a lot of work done to reintegrate it all, to make it all coherent and continuous and logical. But I think that, my joke is, now that I'm home all the time, it's funny because like some people will like clean their house to avoid writing, and I'll write to avoid cleaning my house. I just, I sort of like doing it at some level. But having said that, right now while I'm not writing, I have no idea how I did it, because it seems so hard. And it's like, just sitting in one place and just writing. But at the time, I'd be really enthusiastic, and there was a lot to do. Obviously sometimes it's frustrating, but I would say that at the time I didn't really have writer's block.
And we have more questions from readers regarding cosmology. You obviously are familiar with the latest papers that criticize standard lambda CDM model, though question statistic models of standard candles, LA type supernova. Do you have any idea where scientists can look for evidence of dark energy presence? The energy scale doesn't allow us to look for it in particle physics. Thank you for your answers.
So, I mean, that's one of the things that, I mean, there's lots of dark energy measurements, some satellite things, some, let's just see, lots of places where they're trying to put together, measure what they call W and W prime, measure the equation of state, if it really is dark energy, and is it changing with time. So they're sort of large scale measurements, mostly, to see whether we can, what parameters we can measure. Maybe what you're referring to is the discrepancy in the Hubble parameter, which is really kind of an interesting thing, that measurements from supernovas seem to disagree with measurements from CMB. And that's another, I should say, that's another thing I've been thinking about. You know, it's a really hard problem to solve because we've measured the CMB so well that it's hard to see how we can reconcile this very big difference. But I think it's interesting to see what we can learn in the future from these measurements and also what we're learning now. So, so I think measurements of the Hubble parameter, when they converge, will also be interesting. And there's several different ways that can happen. I mean, even gravity waves will eventually tell us about the Hubble parameter, the rate of expansion of the universe. So it's exciting.
Thank you so much for the time that you found to talk to us.
Thank you, and thanks for your patience and waiting to arrange this interview. It was very nice to meet you. And if you want to write anything by me, let me know. Okay.
Sure. Thank you so much.